Hey everybody, we'll continue chapter 3 and this is 3.9 related rates. So there are some topics in calculus that are challenging and this is one of them. All right, so keep in mind that you need to practice these, and for that reason I solved many problems. So I would recommend to go through them and just practice them over and over until you get the strategy. And when we go to chapter 4, when we go to chapter 4, we will have optimization 4.7, which will be kind of similar task. So if we are this related rates, you have the interest here is you have a rate that you know or can be measured, and you want to figure out another rate that has to do with it or connected to it. So that's the main purpose. So if we are pumping air into a balloon, for example, both the volume and the radius of the balloon are increasing, and their rates of increase are related to each other, right? But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. So in a related rates problem, the idea is to compute the rate of change of one quantity in terms of the other rate of change of another quantity. So the procedure, of course, is to find an equation that connects the two quantities and use the chain rule. And we've done the chain rule to differentiate both sides. There are some examples where you have to do the implicit differentiation, and so we'll see all these. So that's kind of the idea, right? Usually after doing a few problems, we talk about the strategy, but I want to talk about it in advance to make sure that we are following this, whether I state this is 1, 2, and 3 or not, but this is really the strategy in general. We're going to read the problem carefully, understand what it is about, draw a diagram if possible, introduce some annotation and assign symbols, of course, for the variables, the quantities, express the given information and the required rate in terms of derivatives. So you see the rates as from the beginning of calculus, we're talking about the rates, and we got to derivatives, so we're going to express that. Write an equation that relates the various quantities of the problem. So whatever problem we're dealing with, there is some type of equation that governs it. Use the chain rule to differentiate both sides of the equation with respect to t. So here, with respect to time, because it's changing with respect to time. Let's say a distance is changing with respect to time. Substitute the given information into, you see, the step 7. Step 7 is the last one of this substitute, where the common mistake is to try to substitute what's given in advance. So that's why it's important to talk about this at the beginning, which means we will set up the problem, we'll find out what it is and how things are connected, we'll solve for whatever we want. Then we substitute the given information into the resulting equation and solve for the unknown rate. So these are kind of the steps for the procedure. So based on that, the takeaway, what not to do is to substitute the given numerical information too early. It should be done after the differentiation, all right? So here is an example. So the air is being pumped into a spherical balloon. So let's say you have a spherical balloon, and its volume is increasing at V. So when we say now, you see centimeter cube per second, it's not a volume, it's the rate of increase per time. which is what we talked about before, the rate of change. It's like the slope, right? So it is the rate of change here. It is increasing, so it's positive. How fast is the radius of the balloon increasing when the diameter is 50? So this is the problem. When somebody sees when the diameter is 50 centimeters, we'll say, okay, let's just use a D, capital D for diameter here. We'll say, okay, I can substitute that in the formula. So let's break it down. We start by identifying two things. The given information, we're given the rate of increase of the volume, so that's a dV dt 100. The rate of increase of the radius when the diameter is 50, right? In order to express these, so when we say you assign the variable, so we assign V for volume, R for radius, and we need now to connect the two. So the rate of change of the volume is dV dt, so the rate of change of radius is going to be dr dt, all right? So now, of course, what's given is that dV dt, and what is unknown is the dr dt, all right? When, of course, here the diameter is 50 centimeters or the radius is 25 centimeters, right? So what is the governing equation, right? So now we go to this, write an equation that relates the various quantities of the problem. Well, the volume of a sphere is known as this formula V equal 4/3 pi r cubed. So we're not going to use r, right? So we're not going to substitute or anything like that. We need to differentiate. So we will differentiate this V. So we differentiate both sides. So dV, so let's write it here, 4/3 pi r cubed. So dV dt, it's going to be 4/3. This is the power rule with the chain rule. So 3r squared and dr dt. And now the 3 with the 3 will cancel, and we get a 4. So there is a 3 here, and there is a 3 here, and they cancel, and we get that. So what's unknown is this dr dt. So we solve by it or isolate it by dividing both sides by 4 pi r squared. So to get this, we divide. Yeah, I want to show this one, then we do different examples. Divide both sides by 4 pi r squared. Then we get the formula for the rate of change of the radius. All right. Now now you see the last step is to substitute the given information. We have r as 25. We have 4 and pi. We keep it. And most of times you're going to keep the exact form. This is what we call the exact form or value. This 1/25 pi. And because if you use the calculator, you're going to get an approximated value. So this is the main part of this 3.9. So we'll talk about some examples here. So now, here, if a snowball melts so that its surface area decreases at a rate, so the surface area here is decreasing, so kind of the A dt is decreasing. So if you want to write it, is something like this, because decreasing mean negative. Find the rate at which the diameter decreases when the diameter is 11 centimeters. So the question is not about the diameter, it's about the rate in which the diameter is decreasing. So it's similarly, you know, a snowball. What is the area for that? So this is what's given, and you're asked for, let's call it D, and use this, just this capital D for the diameter, right? Right. So the formula, of course, is the area for the snowball here is going to be 4 pi r squared. And we see that we're given in terms of diameter, so let's change it to diameter. We know the radius is diameter divided by 2 squared, which is 4 pi d squared over 4. So it's pi d squared, or somebody will just put it right there from the beginning. But okay, so let's differentiate dA dt. It's pi 2d dt. You do a chain rule on it. The question is to find this the rate for changing of the diameter. So we will divide by 2d and pi, right? And use given information. It's 1 over 2 pi, and d is 11 centimeters, and that's a 5 negative. All right, so it's negative 5, 22 pi. But here for the answer, the way you will say this, of course, is the rate at which diameter decreases when the diameter is 11 centimeters is 5 over 22 pi. All right, so that's the exact value for it. And why we write it positive, because it won't make sense if we say the two words, if we say negative and decreases, right? When we say decreases, it means negative. For number 5, a street light is mounted at the top. So this one is different. It's not really something we're interested in, but since it's unique in its way, we're going to talk about it and show how it is, but it won't be something we're interested in. Mostly the beginning ones, and I'll show the other ones. So here, the street light is mounted at the top of 15 feet here. Let's do it here. Let's say a street light, for example, and 15-foot tall pole, and the man let's say, for example, 6 feet tall, walks away from the pole, so the direction is this way, right? With a speed of 5. So if this is the x direction, then this is the x dt. It's 5, and it's going to the right, so it's positive 5 feet per second along a straight path. How fast is the tip of his shadow moving when he's 35 feet from the pole? So yeah, so this is why so because this one is not similar to the ones mostly you'll see. We're not much interested in it, but we won't talk about it in case yeah, you know, you face this thing. All right, so let's change it. Let's change it. So this is kind of the idea. So you know, draw a diagram when it's possible. If you've done stuff like this, in trigonometry, we would take now this diagram. So the shadow, of course, will be if the light is here, let's say the shadow is here. So maybe we'll call this a distance y, and this person is 6 feet tall, and this one is 15 feet tall. So we can switch this to a geometry sketch. So this is the difficult part with this one. And once you do this, it still becomes not easy to see. So the question is, how fast is the tip of his shadow moving, right? So this part, when he is 35 feet from the pole, so when X is 35 feet, all right? So if we look at it, the traditional example of related rates uses like the Pythagorean theorem, or x squared plus y squared equals z squared, or a squared plus b squared equals c squared. This one does not look like it. It looks like you have a big triangle and you have a small triangle. The large triangle has the 15 and this thing at x plus y, and the small triangle is the 6 and the y. And why they are kind of inscribed, this reminds us, or this picture is of similar triangles. So once we do this and sketch it and look at it, we'll say, yeah, that's similar triangles. So it's hard to see until we do this sketch. And once we do this sketch and we know it's similar triangles, that's going to be useful, because now we can say this part, for example, divided by this part equals to whatever other parts we're interested in. So for example, for this large triangle, this part is going to be over this one. So for similar triangle, if we take, for example, 15 over 6, right? 15 over 6, it's going to equal the distance for the large triangle, which is x plus y, over the same, which is the base here, for this one, y. So that's what will allow us to get that formula, right? So here, that's a 15y equal to 6x plus y. Let's solve for y. 15y, when you distribute this, you get 6y and 6x. So 9y equals 6x. So a y is a 6 over 9x. So which means the y is 2/3 x. So that's the connection between this part and this part. So the y here is a 2/3 x. So once we find this connection, now we can go ahead and try to figure out. So you will see even this example, it's not same as the others, because we will work, it's almost like on one side. So we will say, well, we want to differentiate, so we have to differentiate. Let's change this now. So we have x plus y. We need to differentiate this part because that's the one how far it has to do the moving the horizontal, moving away from the pole, and the y. So we need to figure out first the x. So now we replace x and y with 2/3 x, and we're gonna get something we haven't done before. So this means dx dt, and this multiple dx dt. When we've done this, we never had to actually combine these parts. So we will have to do it here to have a common denominator. So really this is 5 dx dt. And so now what? Dx dt. So we go back, and that's what's given. Right? Dx dt is given. That's why we're looking for dx dt, and we have it. We're trying to find y, but we changed it in terms of x, and we have here it's 5. So so for this example, all right, so 25. So 5 times 5, 25. All right, so that's the rate, x plus y. And again, what is x plus y? It's this point here that we are interested in, how its rate of changing per time. But this point happens to be x and y added together. So that's why we differentiate this x plus y, but we don't know y, so we found it in terms of x. And that collectively gave us something that has the x dt that we know. And we substitute that, and that gives us feet per second. But there is something here I missed, is this 5/3. 5/3, not 5. 5/3, 5/3, 25/3. So that's now the correct answer, 25/3, and the feet per second. All right, so the summary for this problem is you're given dx dt, but you want this part here, how its rate of changing. So you want the x and the y added together. So the question is about this changing, right? And how it's connected to this one. So we try to find y from using, for similar triangles, we'll try to find y, and that gives us the y there. Once we know the y there, instead of x plus y, we will use x plus 2/3 x, right? And that's the work here. We differentiate. It looks like you see something new. What to do with it? We combine it. That's something new we haven't done in the past. This is the first time, so we combine it. It's 5/3, and this is given as a 5, and that's it. So that's done for that one. As I mentioned, it's different in its way. This is a traditional one. Two cars start moving from the same point. Yeah, this one, yes, this is something we're interested in. For example, in engineering, you have different things moving in different ways, and you're interested to find the rate of one in regards with the other. So two cars start moving from the same point, let's say this point. One travels south at 48 miles per hour, and the other travels west, let's say west, at 20 miles per hour. All right. At what rate is the distance between the cars increasing 3 hours later? So this distance here. And so at what rate the distance between these two cars is increasing 3 hours later? So you see, the question here is not the distance. The question is not what is the distance after 3 hours, right? So you see, now this is why it's completely different game, right? What rate is the distance changing? That's what we are interested in, right? So if this is X, so if this is, for example, X, and this is Y, then we know that D squared equals the X squared plus Y squared, right? So if we differentiate this one, I think instead D, I'll use C, just so we can say DD, but just to make it easier, we just call this one Z. So we differentiate, it's gonna be 2Z dZ dt, 2x dx dt, 2y dy dt, divide all by 2, we lose the 2 there. All right. Now divide by z, you get dz dt equal 1 over z, or divide by z or multiply by 1 over z, right? So you get dx dt plus y dy dt. So dy dt is given. It's positive. This one, the x dt is given, and it could be negative because it's on the opposite side. But here we are looking at these rates, you know, in terms of when we switch this, it's going to stay positive. Why? Because we're not really looking at it at a direction in x and y axis. This is more of north, south, west thing, right? So there is no direction of positive, negative. So so if I change back the sketch, the west one and the south one here, so dx going this direction, dx dt is going to be 20 miles per hour, and going this way is dy dt is 48 miles per hour. So looking at it that way, you know, in northeast, we're not saying if you're going east, it's positive, and when you're going west, it's negative, right? And x and y here are just arbitrary variables. We can call them something else, we can say DW here. You know, we can say DW for west and DS for south. It doesn't matter. But I think just the important part is this is the sketch. When you draw it, this is the sketch. We don't have an increase or a decrease here, right, for these directions. So let's look at now the values. So we have dx dt as 20. We have dy dt as 48. And we're missing the x and y and z. So here what we need to do is we need to look at this right triangle and say, well, in at 3 hours, what was the x? So what was now the x at 3 hours? And same question, what was the y at 3 hours? Hence, what is the z at 3 hours? So that's kind of the question we'll ask. If you have 20 miles per hour, at 3 hours, it should be 60 for x. So dz dt. All right, so we have 20x plus 48y, 20x plus 48y. So this one, it should be 20 times 3. And this one, 48 times 3. And that's for the y, and we bring down the 48, and we bring down the 20. All right, so this is the x, and this is the y. We go back to this sketch, the z from the Pythagorean theorem, the z squared equal x squared plus y squared, which means the z is a square root, it's distance skipped positive. It's going to be this 20 times 3, which is a 60 square, and a 48 times a 3, 144 square, and plus a 60, it's a let's just put the answer there. So you need to do a 60 squared plus 144 squared, and take a square root of that, right? And we'll get 156. All right. So this is 1 over 156. All right. So 1 over 156, and all right. So we do 20 times 20 times 3. That's a 1200. And a 48 times a 48 times a 3, that's a 6912. All right. And that's gonna come up to be a 52. And what is this rate of changing? That's mile per hour. So this is mile per hour, right? So as a summary again, for this question, this is a traditional problem. We need, they're heading west and south. That means the angle between the two is the 90 degree. So that's what this states. 20 miles per hour west, 48 miles per hour south. It gives us this triangle. So we need to find this x distance at 3 hours, so it's going to be 20 times 3, and this y distance after 3 hours, it's going to be 48 times 3. We set up the Pythagorean theorem there, we differentiate, we reduce the 2, and we multiply by 1 over z to get dz dt by itself, because that's what the request is. We get this 20x and this 48y. So we replace the x by its value, and we replace the y by its value. Once we do that, we're missing the z. So we use the Pythagorean again to find the z, which is 156. And now the change of rate is 52 miles per hour. So now you can make the judgment. If this one is 20, the other is 48, actually, and it kind of makes sense. The distance between them is changing at such a higher rate, which is the 52 miles per hour. Okay, so this problem comes up in different forms. The ladder 10 feet long rests against a vertical wall. If the bottom of it slides away, so here we have this notation here at the rate of 0.9. So the rate here, dx dt, is 0.9 feet per second. How fast is the angle between the ladder and the ground changing when the bottom of the ladder is at 6 feet from the wall? So this angle here, how fast it is changing when the bottom of the ladder is 6 feet, when x, so this is now based on this, what is the question, related rates here, that's this question when x is 6 feet. So you see the related rates, because it's easier to calculate how x is changing per time, and that should help us find how the theta is changing per time to calculate. So here, of course, what is the connection between theta and x and 10? You know, you start looking into the trig identities. The tangent is you're going to use the y over x. Maybe the sine is the y over 10. We are interested in the x, so maybe let's look into the cosine of theta, which is the adjacent over the hypotenuse. All right, so that step that it says draw the sketch, it's already given. Now find the formula that governs this idea. We don't want any formula, we want one that connects the x and the 10, and the cosine does that. So somebody may start with something else and they have to switch. So now let's differentiate. If you differentiate both sides, for the cosine, it's going to be negative sine theta, right? And this is, of course, is like 1 over 10 times x. So the multiple is 1 over 10 dx dt. And I'm missing the theta dt because we use a chain rule, right? So let's rewrite it. Sine theta d theta dt, 1 over 10 dx dt. So we need to divide by negative sign to get negative sign. So now what are we missing? We're missing a sine theta. So now the question becomes, what is sine theta? We know 100. We know x is 6. Let's just put it there so we can see, or we can do another sketch. So yeah, so we can come up with y. So from x equals 6, and we can call that again z equal 10. We can find that x squared plus y squared equal 10 squared. So y squared equal 100 minus 36. All right, so y is as a square root of 64, which is 8. So the sine theta, which is the y over 10, is 8 over 10. All right. By 2, it's going to be a 4 over 5. And now we can go back to this thing here and substitute. So let's write it d theta dt. And you know, when you divide by a fraction, 4 over 5, it's going to be a reciprocal. So if you put a 4 over 5 here, we have these dx dt. Dx dt is given, it's 0.9. All right, so if you want to keep it, you can do negative 40 over 5. If you put over 1, you multiply these. Then 1 over negative 8, 0, 9. So it's 0.9 divided by 8, which if you want to remove the decimal, you'll multiply by 10, and you get negative 9 over 80, right? And the change of angle here, it cannot be, of course, in degrees. It has to be in radians because of the units. So, so what is the answer again? So keep in mind the way you state the answer is the rate is negative 9 by 80, but we would say the angle's rate of change, the angle's rate of change when x equals 6, right? That's what's given there, is 9 over 80. So you will enter 9 over 80 as exact form for this question. A similar type of problem, but as I mentioned, these are the ones kind of we're interested in, and they're now similar, but we're going to look into some details here. Yeah, so I did, yeah, so I already solved this one, but I need not, I think I put this here to show you, where is it? Yeah, so just, if you have to use, you know, these are the common derivatives we use. So we may have to use cotangent later on. Derivative, it's here. And of course, if you need to use the tangent or something, derivative is there. So this is done. All right, so a kite example. It's a little bit challenging because you know, how do you deal with this? But really, you have to look into something fixed, And based on this kite is 100 feet above the ground. So that's these 100 feet is going to be fixed because it's going to say at what rate is the angle this theta is changing in radians between the string and the horizontal when 200 feet of the string, so there, have been let out, right? So, and the kite is moving horizontally in this direction, right? So what it is that's given, what is this 8 feet per second? So it moves horizontally. So dx, if we call this the x distance, it's dx dt equal 8 feet per second. And the question again is this angle theta. So we used cosine for that example, and now what can we use for this example? So some will start with the tangent, some will start with cotangent. It doesn't matter. I think if you do tangent, let's start with the tangent to show. You're going to do 100. Wait, this thing's stopping. You're going to do 100 over x, right? Then you will get x as 100 over a tangent theta. And we know 1 over tangent is cotangent, so 100 times cotangent theta. So it doesn't matter how you start, you will end up with this 100 cotangent theta. And that's going to give you the governing formula or equation for the problem that you're going to work with. So we always, you see in these problems, we need some type of equation that represents the problem. And once we have that, we differentiate. So the next step is going to be to differentiate, and you get dx dt. The multiple is 100. Now the cotangent, that's why I posted this one, is negative cosecant squares. All right, so negative cosecant squared theta, of course, the theta dt. Okay. And the question is about the change of theta with respect to time. So we will divide by negative 100 cosecant square theta, both sides, to get dx dt. So we will divide by this quantity both sides to get dt, d theta dt on one side. And if you want to simplify a little more, we know that 1 over cosecant theta is sine square theta. So if you want to use the terms of sine, that's a nice switch there. Of course, we can put a note here as well, this one. Yeah, and once we get here, we want to find what, so the question again, what is sine theta? Well, we're going to look at the triangle. Sine theta is going to be the opposite over the hypotenuse, which is 0.5. And let's replace it. 0.5 squared divided by negative 100. Dx dt is given, all right. that's given already. That's the 8 times the 8. So d theta dt is going to be, so that's squared here, right? Yeah, so 0.25, 108. So we get 200, and we get negative 1 over 15. That's 15. So, we write it again, the rate of change, of angle is 1 over 50 radian per second.